Hello, everybody. Yep. So my name is Timothy Wong. So I am from CENTRICA. CENTRICA is an energy company in the UK. Yep. So who we are? So we are an energy company based in the UK, and we serve a lot of customers. So we provide different kinds of services. So for example, we build smart thermostat, we supply energy, we explore energy and all that. Yeah. But one of the most important things I want to talk about today is about energy service. And in this case, I'm talking about boiler servicing. So one of our most important services is to fix people's boiler. So for those who don't know, a boiler is a device that keeps people warm, and it burns natural gas, yeah, in people's homes, and it breaks all the time, right? So we as a company, we help people fix that, yep. And in order to do that, we have a lot of engineers who works for the company, and in order to provide the service, we need to schedule the capacity correctly going forward into the future, right? So that's what we do. Yeah. So we need to predict that going forward. So we use certain modeling techniques here, which I'm going to go through today. Yep. So the whole problem, as an overview, the whole problem is about predicting appointments going forward into the future. Yeah. So let me go through several concepts first. Yeah. So when a job is created, a job is that a boiler is broken. That is called a job. Yeah. But a job doesn't equate an appointment. Job and appointment are different things. Yeah. A job normally requires several appointments in order to close, complete, and resolve. For a very simple reason, because in the first appointment, sometimes the problem is too complicated. You need a return visit, or in the second appointment, you still don't have enough parts and you need more time. Time is running out, so you need a third appointment, and so on and so on. So what I'm saying is that there are several concepts here. Jobs is different from appointment, and one job requires several appointments to resolve. But for our application here, so we are forecasting appointment, but also knowing the number of appointments still not enough, because we need to predict our capacity going forward into the future, right? So we are predicting actually the amount of time required for each appointment going forward into the future. So ultimately, we are predicting number of hours required for a particular day at a particular geography. Yeah. So for example, on a particular day, we require 500 hours working hours in this geography, and for other location, we need 600 hours, for example. Yeah. So that's how the problem is structured. Yeah. So clearly there are several steps here. Yeah. So step number one is, of course, to predict how many jobs are there going forward into the future, number of jobs. But one job, as I said before, requires multiple appointments to complete, right? So from jobs to appointment prediction, that's step number two. Once we know how many number of expected appointments are there in the future, then we convert that into the amount of time. Yep. And then ultimately we add them up, then we get our ultimate capacity forecast into the future. Yeah. When I say future, it goes into the future. It's like around several weeks. Yeah. We are talking about weeks at daily level. Yeah. And obviously we serve most places in the United Kingdom, and in this case, we are modeling at the local geography level. We call them surface patches. So we repeat this modeling process for each geography, for each patch. Yeah. So that's how we structure the problem. So let's go through the algorithm very briefly. Yep. Right. So step number one is about job modeling. Yeah, job modeling. So what is a job? A job is a broken boiler, a broken device, yeah, something that requires attention. Yeah. And in this case, we are dealing with gas boiler, as I said before. So the job demand is clearly driven by many external factors like weekday, weekend effect, calendar effect is important, right? It depends on people's behavior. It's also driven by other external factors like weather, seasonality. Yeah, people use it more often in certain conditions, and therefore it breaks more often, right? So that makes sense. So it's driven by many other factors. And then by understanding these factors, we can predict the job demand. Yeah, so that is step number one. So as I said before, here we are looking at the number of job demand. So it's a number of things, a count of things. So the first thing we do is to look at the distribution, right? So this is a Poisson distribution. The number of jobs follows a Poisson distribution, and there are certain tests that we can apply to. So for example, there's a VCD package, and you can apply a chi-square goodness of fit test to test for Poisson distribution. Yeah. So so once we understand that, okay, so this is a Poisson distribution, so what kind of modeling techniques can we apply to this kind of data? Yeah. So therefore, a Poisson GLM, right? So we simply use the GLM function and specify the family as Poisson. Yeah. So therefore, we get a Poisson GLM, right? So that's the first thing we tried. It's good. It works. But clearly, there are improvements, right? In this model, let's go through a bit more details about the model. So the thing that we are modeling is the number of jobs, which is there on the screen as green lines at the bottom. Yeah, so the bottom is green, if you can see it. Yeah, and clearly it's correlated with many factors. So for example, it's inversely correlated with temperature. Yeah, there's a causality effect there. If it's cold, then people burn more gas. If people use the device more often, then it breaks more often. So there's clearly certain causality effects there. Yeah. So when we train the model, we divide it into training set and testing set. Yeah. So roughly 2 years training set and 1 year for the testing set. Yeah. So that's what we do. This is only one of the input variables, and there are several of them, like wind speed, rainfall, solar radiation, and all that, because there are solar heaters and yeah, all sorts of things that are driven, that are driving the number of jobs here. Yep. So one of the improvement is to use GAN models, so Generalized Additive Model. Yep. So a GAN model is very similar to traditional regression, with the exception that it uses smoothing splines. Yeah. So traditionally, we would use a linear model, and then you specify polynomial effect to make it more smooth, right? So a GAN model uses smoothing spline to resolve that problem. So you just use the term S bracket and then your variable. Yep. And then the GAN model would learn the smoothing spline there. Yeah, so on the right-hand side, there's a visualization, a ggplot, showing how the spline is. Yeah? So on the x-axis is the input variable, on the y-axis is your response variable, so that's your smoothing spline. Yeah? So the spine is based on a combination of basis function, and basis function is what constitutes a smoothing spline. Yep, so that is a GAN model, and that is the second thing we try in modeling the number of jobs. Yeah. So I'm comparing with GAN model, comparing with GLM. So we've run a very simple comparison. So in terms of AIC, it's slightly lower. So slightly lower AIC means a simple model is good, right? So yeah. We've also run an ANOVA model, an ANOVA test to check the different, check these two models, yeah, and the residual is significantly lower, statistically significantly lower, so that's also a good sign, yeah. Another improvement we've tried is to use interaction effects, yeah. So in GAN models, you can use the tensor product, the TE bracket, and then variables there to specify interaction effects between different variables. And this is just an example. So in this case, we're looking at boiler breakdowns demand, right? Yeah. So it's a very well-known interaction effect that it is driven by temperature and also wind speed, because if it's cold, but if you got strong wind on a very cold day, then you got extra demand because people feel colder. Yeah, so that's an interaction effect there, and this is how we can model it. And there are other packages that can help you visualize it. And the right-hand side is the output of the visualization. But I'm not going to go through that in details. Yeah. So as I said before, step one is to model the number of jobs, right? So I'll go through very quickly how it looks like the results, yeah, how the result looks like. So as I said before, there are many, many local surface patches, local geographies, and we can't visualize all of them because there are hundreds of them. So, but we can look at a few of them. So this is, what you're seeing there is a London area. So there are lots of box plots on the screen right there. Yeah. So the box plot is showing the distribution of the model it's not the model residuals. The box plot is showing the distribution of the MAPE, the model accuracy, in the training set and also in the testing set. So training set is in blue color, testing set is in red color. So you can see that the distribution between training set and testing set are quite consistent. They are comparable, and also the distribution across different patches are also quite comparable graphically. We've also got numeric results in a table, but I'm not going to go through that in too much details. Yeah? So this is at patch level view. We've also aggregated everything into the whole country and look at how that compares. Yeah? So on the left-hand side is training set, on the right-hand side is testing set. Blue is the model. Red is the actual observation, so they are quite close. Yeah, when we aggregate them into the whole country. So this is the summation of all the local geographies. Yeah. So this is step number one about job modeling. There are several ways to improve it. So, for example, one of the most common way is in fact to handcraft different features and turn these nonlinear features into linear features, and therefore you can use traditional techniques like linear regression. So forget about GAM. It's a really traditional technique, but it's still quite it's quite popular in the energy sector. Yeah. So in our approach, we model the geography separately using separate model. Yeah. So another improvement is to use multi-level regression, and you can specify the geography as groups. Yeah. So that's another improvement, and there are other modeling techniques that we can try. So for example, ARIMA, time series approaches, or RNNs. Yeah. So that's improvements for step number one. Step number two. So once we know that the job demand is still it's not our end goal. It's only intermediary product. Yeah. We want to understand how much time do we need, right, for going forward in the future. So we use the job demand to predict how many appointments do we have in the future. Yeah. So that's step number two. So as I said before, a job requires multiple appointments to resolve. Yeah. So the number of appointments created by a single job is normally is always higher than one, but it can be very high. Yeah. Of course, we as a company, we want the number of appointments to be as low as possible, right? But in some cases, it can be 2, it can be 3, it can be more. Yeah. So it's dependent on many things like which day the job was created, which day the appointment is booked. So it's driven by a lot of categorical variables like calendar effects. That's what I'm talking about. Yeah. So let's look at the appointment booking data set. Yeah. So on the left-hand side, we are looking at a table. So this table shows a list of job IDs and appointment IDs. So a job is created on a certain date. And for this particular job, there are several appointments associated with it. Yeah. So just like I said before, a job is associated with multiple appointments. Yeah. So if we run a descriptive chart, yeah, using all the appointments in for example, in over a year. So we'll get an overall appointment booking pattern as indicated in the red line. Yeah. So on the x-axis of the red line chart, you're looking at the number of days ahead since the job was created, and on the y-axis of that chart, you're looking at the number of appointments that was booked. Yeah. So more appointments being booked in recent days because people want things sorted quicker. So people prefer having appointments in day 1, day 2, day 3 ahead. Yeah, simple, understandable, right? And as time increases, there are less and less appointments. So that's an overall booking pattern. But if you do a subset, for example, you subset all the appointments booked, all the appointments that has a job created on a Monday, yep, jobs landing on a Monday. That is what you will see if you plot the subset of the entire data set. Yeah? You see a clearer booking pattern. So for example, there on the blue line, these are the jobs created on a Monday. So you can see a 7 days seasonality there. So there's a 1 week because there's less jobs being created, less appointments being booked on a weekend. So you see a big drop at around day 6, day 7, and another drop around day 13, 14, yeah, and so on and so on. So that's what I call an appointment booking curve. Yeah. So a bit more about data transformation and how you model it. Yeah. So we talk about the data set and the curve. So so we are trying to identify what is an appointment and what is an observation. Yeah. So in this case, we are trying to calculate, predict, to model the number of expected appointments going forward in the future. Yeah. So we need to know on what date the appointment was booked, but also on what day the appointment was not booked. So not booking appointment is also an observation. So despite we have a full data set on the left-hand side, we still need extra steps to transform the data set to show us which day the appointment was not booked. So in this case, we actually had to expand the data set by a lot. Yeah, although the data set seems quite sparse, yeah, because most days we don't book an appointment. Yeah, but that's how the data set is structured. Yeah, so on a particular day, on the purple table there, you're looking at which day the appointment was booked. Yeah, and then we convert them. We do like a unpivot table, turn it back into a narrower format, and this table, the black one, goes into a random forest model. Yeah. So as I said before, the data set used to be small, but once it's been transformed and expanded, the number of rows is actually quite a lot, plus all the extra variables that we calculate in this table. So the number of columns features is around 10 to 20-ish. Most of them are categorical or ordinal variables, factors, yeah, based on calendar effect. But the size of the data, the length of the data set is actually quite large, and it's actually between 300 to 400 million rows. So it's kind of a big, so-called big data problem. Yeah. So what we do is we use Microsoft R. Yeah. So inside Microsoft R, there's a function called RxD forest. So it's a random forest, yeah, but it scales. So it deals with the data in chunks. So despite we're having 300 million rows, the function and the algorithm will chop it off into smaller chunks. Therefore, the whole data set is actually stored either on a big data system like Hadoop, or it can be stored on a hard drive on your C drive, for example. And then it deals with the data set in chunks, so that it doesn't blow up the memory. Yeah? So that's how we deal with it. This is how the appointment booking curve looks like. This is the modeled results. So in the model results, you're looking at a gradual decline in the number of appointments, which makes sense, and more appointments being booked in recent days, so less than day 7, so 1 week. Yeah, so it drops significantly after 1 week, and it also drops even further on public holidays like Easter holiday and other bank holidays. So this is how the result looks like. Yeah. So at this step, this is step number 2. We know about the number of expected appointments, and also from step 1 we got the number of expected jobs. Yeah. So we simply multiply them together. We will get the total number of expected appointments. Yeah. And also, this is how the model result looks like. Yeah, this is daily level. We turn them into weekly and monthly for easier visualization. Yeah, so people can look them a lot easier. The last step is to estimate the appointment duration. So appointment duration has 2 types of duration. So travel time and the job time. So, but when we look at the data set, the appointment duration hasn't got a very clear correlation with with any variable. So we run a correlation plot with different variables. It's not driven by any of them. So what we really use is, in fact, a rolling mean to estimate the travel time and the job time. And once we got the time, the last step is to apply it in a real setting, and the real setting is an ensemble model. Yeah, so we subscribe to an ensemble weather forecast model. We apply everything, and in the end, we got an ensemble forecast. So an ensemble forecast has 50 members, and this is how we run the model. Yeah, so you can see a clear pattern over 2 weeks' time. This is around 14 days, and we can also extend it further to 90 days. And that is what I want to talk about today, and thank you very much.